All right, so we're in section 8.1 today. Sequences and series. So sequences and series are, we'll talk, what we're doing is kind of an introduction to sequences and series. When you go on to calculus, sequences and series are a really important topic in calculus. So it's important that we have some understanding of them now, and it's nice. There are things that we can do with sequences and series that are kind of nice and make them interesting to work with. So today is a lot of terminology and understanding what we're talking about when we're talking about these things. So a sequence is basically a list of numbers. Now it's not just a random list of numbers. What we're doing is we're starting usually with, we usually use the positive integers, 1, 2, 3, 4, 5, and we talk about the first number, the second number, the third number. So each number in our list has a relationship to the numbers 1, 2, 3, 4, 5, etc. We call each number a term of the series. So we talk about the first term, the second term, the 10th term, the nth term. So each individual number is a term. The way we usually write them is we'll say a sub n. And the n refers to where it is in the series. So a sub 1 would be the first term in the series. A sub 10 would be the 10th term in the series, etc. If we put a sub n in braces, this is talking about the entire series. I'm sorry, the entire sequence. So this is all of the terms. So when we just have a sub n, we're talking about one term. When we have a sub n in braces, we're talking about all the terms in the sequence. So as an example of a sequence would be the Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13, etc. So this would be a sub 1, a sub 2, a sub 3, etc., etc. First term, second term, third term, all of the entire Fibonacci sequence together would be written in braces like that. So a couple of things that we're going to do with sequences. We want to, usually we're given a formula for the nth term of a sequence. So we want to use our formula to write out the terms of our sequence. We will want to start with a sequence and be able to write a formula for the nth term. And then there are special kinds of sequences that have nice things that happen with them, and we can calculate things with them easily. So that's what we're going to do. So let's look at a couple of examples of writing out a sequence if we know the rule. So questions so far about what a sequence is. Okay, so let's write a few out. So on these examples, we want the first four terms. And we'll start with an easy one. A sub n equals 2n plus 5. So when we have a rule like this for our nth term, we're using the positive integers to plug into our formula. So we're starting at 1, 2, 3, etc. And if we want to be more technical about what a sequence is, we usually say that a sequence is a function whose domain is the positive integers. So I'm plugging in positive integers. So for this sequence, A sub 1 is 2 times 1 plus 5, which would be 7. A sub 2, 2 times 2 plus 5, which is 9. A sub 3, 2 times 3 plus 5, 11. And a sub 4, 2 times 4 plus 5, which is 13. So the terms of this sequence would be 7, 9, 11, 13, etc. So that's how we find our terms. And we can define our terms. We can have all kinds of different rules for our nth term. And the more interesting sequences usually have more complicated rules. Let's look at another one. Let's say that b sub n is 3 to the n minus 1. And we want to write out our 4 terms here. So b sub 1 is going to be 3 to the 1 minus 1, which is what? 1. 3 to the 0 is 1. b sub 2 is 3 to the 2 minus 1, which is 3. 3 to the first. b sub 3, 3 to the 3 minus 1, which is 9. And b sub 4 is 3 to the 4 minus 1, which is 27. So that would be our first 4 terms of the sequence with this for the nth term. All right, this one a little different. So before we write out our terms here, what is this minus 1 to the n? What is that going to do to the terms of our sequence? So you had the right, you were doing alternate.
Yeah.
So the signs are going to alternate, right? Because minus 1 to the 1 power is negative 1. Negative 1 to the second power is positive 1. Negative 1 to the third power is negative 1. So this is going to alternate signs. So when we have something, when we have negative 1 to the n or negative 1 to the n plus 1, etc., etc., we're going to have alternating signs. So c sub 1 is minus 1 to the 1 power over 1 squared plus 1, which gives me minus 1 half. C sub 2 is minus 1 squared over 2 squared plus 1, which is going to be positive 1/5. C sub 3 minus 1 to the third, so we'll get a negative sign again. 3 squared plus 1, which is negative 1/10. And C sub 4, we'll get our positive term again, negative 1 to the fourth. 4 squared plus 1 is going to be positive 1/17. So those would be the first 4 terms of that sequence. Now thinking about what we just did here with this minus 1 to the n, what if we wanted our first term to be positive and our sequence to alternate signs? How would we set that up? So if we have minus 1 to the n, that made our first term negative. How can we get the term with n equals 1 to be positive? Negative 1 to the n minus 1, or we could also do negative 1 to the n plus 1. So that would make our signs alternate still, but we'd start with a positive rather than a negative. So anytime you have a minus 1 to the n, minus 1 to the n plus 1, and minus 1, you're going to alternate signs, and one's going to have the odd terms negative, like this one does, and the other would have the even terms negative, if we had an n plus 1 or an n minus 1. All right, questions on writing out our terms? So this will be one thing that we want to do, is be able to write out terms of sequences if we have a rule for the nth term. So the more interesting sequences often have to do with factorials. So I want to talk a little bit about factorial notation. So who can tell me what is our symbol for factorial? Exclamation point. It's a nice symbol. N factorial. And do we remember how we calculate factorials? Every number from 1 to n multiplied together. So this is going to be 1 times 2 times 3 times ... up to n minus 1 times n. So every number between 1 and n multiplied together. Factorials are only defined for n as is a positive number. Factorials aren't defined for negative numbers. And we say that by definition, our definition of 0 factorial is 1. So in order for everything to work out the way we need it to, 0 factorial has to be 1. And the factorial symbol takes the same place in the order of operation as exponents. So we would do factorials after parentheses. So they're in the same place in the order of operations as exponents. So for example, if we wrote 2 times n factorial, what this is 2 times n factorial. So we would do the factorial before we do the multiplication. And that would be 2 times 1 times 2 times ... up to n. Where 2n quantity factorial is 1 times 2 times 3 times ... to the up to 2n minus 1 times 2n. So all the numbers between 1 and 2n multiplied together. So here we do the parentheses first and then the factorial. So if we had a sequence that was defined that our rule had factorials, we would be able to write these out. But before we do that, 0 factorial. We said 0 factorial. I just want to look at some factorial. 0 factorial is 1. What would be 1 factorial? 1. 2 factorial is 2. 3 factorial, 6. 4 factorial, 24. 5 factorial, what is it? 120. 6 factorial, 720. I'll stop there. So factorials get very large very fast. 10 factorial is a huge number. So let's look at a sequence where we have a term, our terms defined by factorials. So let's say we have a sub n equals n squared over n factorial. And we want the first 4 terms. So a sub 1 here, what would a sub 1 be for this sequence? 1 squared over 1 would be 1. A sub 2 would be 2 squared over 2 factorial, which is 4 divided by 2 is 2. A sub 3. 3 squared over 3 factorial. What does that come out to? What is it? 96, which reduces to 3 halves. And then a sub 4 is 4 squared over 4 factorial. 16 over 24, which reduces to 2/3. So that would be a sequence defined using factorials to define the term. And there are some very interesting sequences that end up with terms that involve factorials. The other thing that we'll have to do when we work with factorials is simplify factorials. And factorials are fun to simplify because you get to cancel out a lot of things. So let's take a look at a couple of examples of simplifying factorials. When we start talking about probability, simplifying these factorials is going to be a tool that we use in probability. So we want to simplify these. Uh, 10 factorial over 2 factorial times 8 factorial. So we want to be able to simplify this without having to calculate all of this out. And it simplifies pretty nicely. So what are we going to do here to simplify this? So with small enough numbers we can write these out. So this is going to be 1 times 2 times 3 times 4 times 5 all the way up to 10. It gets more complicated when the numbers are bigger. Well, 2 factorial is just 2. And 8 factorial is 1 times 2 times 3 times 4 all the way up to 8. So what can I do here? Cross out 1 through 8. This whole thing divided by this whole thing is just 1. The 2 I can divide into the 10 and make that 5. And we get 9 times 5, which is 45. The other way we can think about this is 10 factorial is 8 factorial times 9 times 10. Everybody see how I can rewrite 10 factorial that way? 8 factorial is 1 times 2, da 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 da, all the way up to 8. And then to get 10 factorial, we multiply that by 9 and then 10. That's what I've got written here. Divided by 2 times 8 factorial. Well, 8 factorials cancel. The 2 I can reduce the 10 to 5 and I get 45. So we can always write a bigger factorial in terms of smaller factorial numbers to help us simplify. So that's going to be nice when we're simplifying something like n factorial over n plus 1 factorial. So we can think about this in a couple of different ways. I can rewrite this, like I did up here. So this is 1 times 2 times 3 times dot 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 all the way up to n minus 1 times n. All the numbers between 1 and n. And in the bottom, I have 1 times 2 times 3 dot 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 times n minus 1 times n plus 1. All the numbers between 1 and n plus 1 multiplied together. So what can I cancel out here? Everything up to n plus 1. So I cancel that, and this is just 1 over n plus 1. And I can think of this as n factorial times n factorial times n plus 1. All the numbers from 1 to n here, and then I'm multiplying by n plus 1 to get that n plus 1 factorial. And those cancel, and I get 1 over n plus 1. Questions on how I did this? All right, so let's look at, let me have you think about this one. So how would this simplify? Yeah. N squared, so Jonah says n squared plus n, so factor. So factor that out, so how would we write it without distributing? Right. So this would just be n times n plus 1. Because in the denominator I could rewrite this, I'm going to put this down here, I could rewrite this as n minus 1 times n plus 1. Sorry, n minus 1 factorial times n plus 1. That's all the numbers from 1 up until n plus 1. And then in the denominator I have an n minus 1 factorial. And those cancel. And that's n times n plus 1. So when we're simplifying factorials, we end up with lots of cancellation. Questions there? All right, so the other thing that we're going to do with sequences is we want to, if we have all of the terms or we have several terms of the sequence, we want to be able to write the rule for the nth term. So let's look at a couple of examples of doing that. So we want to write a rule for the nth term. So we're kind of going backwards from what we did with our first example. So here are the terms of our sequence. 0, 3, 8, 15, ... So there are the terms of our sequence. And we want to write a rule for the nth term. So what we're trying to do here is come up with a relationship between where the term is in the sequence, first term, the second term, the third term, and the number we have here. So anybody have an idea of what kind of rule? So what do you think, Emily? So you're saying 2n minus 1?
Yeah.
So this would be 3. That would be the third term. 2 times 3 is 6 minus 1.
Squared.
Okay.
Yeah.
So you're saying n squared minus 1.
Yeah.
Okay. Does that work? N squared minus 1. This is 1 squared minus 1. 2 squared minus 1. 3 squared minus 1. 4 squared minus 1. Looks good to me. So my nth term here would be n squared minus 1. For the terms that we have here, this rule would work. If we got more terms and the pattern changed, then we'd have to work a little harder. But for the 4 terms we have, this looks like a perfect rule. So we want to find a relationship between the term and the number that's in the term. Let's look at another one. How about 1/2, 1/6, 1/24, 1/120th, ... Does anybody recognize this? So what are these? What are these numbers? These are factorials, right? These are factorials. Is it n factorial? 1 over n, is it n factorial? 1 factorial is 1. N plus 1 factorial. Because this is 1 over 1 plus 1 factorial, 1 over 2 plus 1 factorial, 1 over 3 plus 1 factorial, etc. So that rule would be 1 over n plus 1 factorial. This is fun to me. I like it. Let's look at another one really quickly. Minus 2/3. 3/4. Minus 4/5. 5/6. Minus 6/7. So first off, what do the alternating signs tell us? We're going to have a what's going to be part of our nth term? Minus 1 to the n. That's going to give us, this is going to give us our alternating signs, the minus 1 to the n. And then what kind of rule can we find that relates the fraction to our terms? N in the numerator, what do we want to have? N plus 1, does that work? This is 1 plus 1, 2 plus 1, 3 plus 1, 4 plus 1. N plus 1. And in the denominator? N plus 2. Minus 1 to the n times n plus 1 over n plus 2. And that would give us that sequence. Questions there? All right, the last thing we need to talk about, when do we finish today? Oh, we're doing well. Is summation notation. So what we're going to do is we're going to talk about sequences, we're going to talk about the numbers, and then we're going to add those numbers together. We want to add them together. And that's what summation notation tells us. Summation notation looks like this. Sum I equals 1 to n, a sub n. This symbol here is a sigma. It's actually a capital. It's a Greek letter sigma. And when we see it in this context, it means to add together. This tells us to add the terms of the sequence. So the summation, sum I equals 1 to n of a sub n would be a sub 1 plus a sub 2 plus a sub 3 plus dot 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 plus a sub n. So we're adding all the terms of the sequence together to get the sum. We call I the index. So it just tells us which term we're talking about. 1 is the lower limit. For this particular example, we could pick any number greater than, from 1 on up to be our lower limit. And n is called the upper limit. So we're just adding, now we're just adding the terms of our sequence together. When we add the terms of our sequence together, we get what we call a series. So let's look at an example of a summation. Let's sum I equals 1 to n of 3i. Or sorry, 1 to, I want to go from 1 to 4 here, not 1 to n, 1 to 4. So this is just going to be 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4. And we calculate those out, add them together, and we get 34. So we're just adding those 4 terms together. So when we see the summation notation is just telling us to add. A couple of properties of summation. Nothing really complicated, nothing really earth-shattering here. It's just because we're adding, if we have each term multiplied by a constant, we can factor out that constant. And this should be a sub I. And C is a constant. So I can factor that out. I can add or to subtract 2 sums from each other. So the sum I equals 1 to n, a sub n, plus or minus the sum I equals 1 to n of b sub n. I can just add each term together and have one sum. So I don't have to add them together at the end. I can add them term by term. So a couple of properties of sums. Now I said when we add these together, when we have this sum, we call this a series. We add the terms of our sequence, we come up with a series. If we add an infinite number of terms, we call it an infinite series. 1, 2, this should be infinity. And we'll talk about at least one special infinite series that we'll do a little bit of work with in a couple of days. So infinite series, depending on how we set them up, they have some interesting properties. We can sum an infinite number of terms and get a finite number. We don't always get infinity. Sometimes we do, sometimes we don't. If we have an infinite series and we sum only a certain number of terms, so we call sum I equals 1 to n, a sub n, the nth partial sum of the infinite series. So an infinite series means we add all of the terms together. A partial sum means we add only a certain number of terms. So we could have the 4th partial sum. So what we did back here, where we added these from I equals 1 to 4, if this were an infinite series, this would be the 4th partial sum of this series, because we added 4 terms. The 10th partial sum would be adding 10 terms. The 100th partial sum would be adding 100 terms, and so on. When we have a little bit more time in class, maybe on block day, I will show you how to do some of these things in our calculator. Our calculator will do some of these things nicely. Not the infinite sum, but these partial sums we can calculate quickly and easily in our calculator. All right, so let me take a quick look at an infinite series that that has a finite sum. So let's say we had the summation I equals 1 to infinity of 1/10 to the I. So let's write out some terms. So this is going to be 1/10 plus 1/100 plus 1/1000 plus 1/10,000. How can we write this 1/10 as a decimal? Point 1. How about 1/100? 0.01 plus 0.001 plus 0.0001, and I'm going to keep going, plus dot 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 dot. If I keep going with this pattern, what does this number turn into? 0.11111 dot dot dot. So this infinite series would sum to 0.11111. So we're adding up an infinite number of numbers, and we get a finite number. In fact, we get a fairly small finite number. So that would be an example of an infinite series that has a finite sum. And we'll talk more about these. All right, questions? Okay, the homework. It looks like a lot of problems. A lot of them are calculating terms of series, finding a rule for the nth term. So not a lot. They're not intensive. They're not long. They shouldn't be complicated problems. So they should go pretty quickly. There we go. And I worked really hard to make sure